thank you for the invitation. That's a delightful meeting for reasons which are obvious and on which I would expand later also. The official title of my talk, at least as it's presented, is the metric graph extension of the Ising model with applications. The subtitle is the virology of Ising model, a concept which I would explain. And specific examples of metric graph versions of Ising systems can be found in the contact process, where the continuum is that of time, not space-time, but time. There's a continuous time, one-dimensional Ising model, which was introduced by Anderson, Yuval, and Haman. In a way, it was related to a talk which was presented yesterday, long-range Ising systems. Then I will talk about the quantum Ising model. Again, the continuum is just the time direction, or at least imaginary time. And other more general approaches. There's a general approach to quantum systems, which, as is generally known, reduce the study of the ground state of a quantum system in d dimension, say of a d-dimensional lattice, to a version of statistical mechanics, stat-mech problem in d+1 dimension, where the extra dimension is again continuous. And then there is the Villain model, which is related to the most recent work with collaborators, over which I should mention some results. So a comment about this virology. It's some time ago that we noticed that the Ising model can be regarded as the Drosophila of statistical mechanics. Drosophila is this tiny fruit fly, tiny even as flies go, whose molecular structure, for which the molecular structure of DNA and all that, and the process of development actually contains the secrets of, say, even human evolution, just as is well known. I mean, in general, the way organisms develop from the information-packed DNA. Then, in addition, viewing how the ideas propagate within our community and our understanding and grasp of Ising model and other topics brings to mind concepts of virology, where viruses are those ideas which hop from one mind to another. They replicate, they develop, they mutate, and then hop on, and that's how viruses get to be really viral. And you would see this in a way. What I wanted to do is present a couple of examples where you see this process at work. I mean, this being the 100th anniversary or 100+ anniversary of the Ising model, as somebody already commented, at a birthday you usually also make some comments about the lifespan of the individual or the subject. So what I'm saying is should not be presented as a thorough development of the subject, for which 1 hour does not suffice, and I'm not fully qualified. But some themes which are close to works which I've been aware of and did in the past, I will present here. So, examples of some. Let's see. Let me start by mentioning those examples. So, the contact process. Or actually, sorry, before I get there, it may be better to make some more general comments before I get to that. Just to get a map of what I hope to say, to comment on. As I mentioned, ideas have evolved, developed by moving from one stat-mech system to another and to yet another. And it's been very fruitful in the connection between Ising and percolation is a good example of how actually your understanding develops if you do not limit yourself to one model, but keep asking how do things look from another perspective. Certain things are very natural for Ising systems, but then you may ask if there is any analog of that in percolation model, which on face of it is a very different model. And then you discover the analog of that, and that's a new result here. But then this suggests, by arguments which are native to percolation, some other results. And then you ask again, well, what's the counterpart of this here? And you find it. And the step which is accomplished by going this way and back is something which would have been surprising had you just stayed in this domain. And then, as is known in particular in this community, Ising and percolation are just 2 points of Q-state Potts models for which there is a parameter Q, and Q goes from 0. Well, it's actually, for the brave, Q even be negative. And yesterday people asked about complex, but in this modest presentation, Q would be non-negative real. For Ising model, let's see, Q equals 0 is percolation. Sorry, Q equal 1 is percolation, excuse me. 2 is Ising. Another notable value is Q equal 4, where something else happens. So these are Q-state Potts models. And again, this sort of an interplay has been very fruitful. Then out of this emerged also the relevance of what may be referred to as the loop soup models. Actually, I think that I used the term loop soup models when I was looking at the way back at the Ising model, whose partition function can be written as sum over configurations, some with some appropriate weights, of configurations of what may be regarded as flux numbers of loops over a graph. And my son was very young. He was eating breakfast with the alphabet soups, where little alphabet letters were floating in milk. And I think based on this, I started to refer to these things as loop soups. And the concept, probably independently from the term, but it really developed into a fantastic mathematical object about which we heard in the presentation of Van Lien-Werner. So there is also the continuum theory of loop soup models, which is very rich in mathematics and with applications to stat-mech models that we heard about. Then there are also quantum and classical loop models. And I would like to mention before the end of this talk an example where the same or very similar and essentially the same random loop ensembles have project onto a variety of models with very different physics. That would include quantum spin chains for which the phase transition of relevance is dimerization, the XXZ model for which the phase transition is in terms of long-range order under certain conditions, and the same loop soup, so to say, actually projects also onto classical Q-state Potts models. And the phase transition here is a very different nature, which was also already mentioned in this talk. All of that is related to a common mathematical scaffolding supporting these different, physically different models. So that's this notion of virology, how ideas get enriched by hopping from one subject to another and from one mind to another. And there is this process. Here I'm describing it in the context of Ising and related models, but it may actually be a paradigm of what's happening in our science more generally. That's how we approach the mental, our thinking of science, I think. So, of course, there is experiment also. I do not want to say that it's a totally mental exercise. Many of the phenomena we are talking about actually were driven by experimental observations. And it's we notice things when we have the language for it, and we develop ideas, and it's this process which I refer to. Okay, let's see. Oh, I wanted to mention contact process, so we have some examples of what we are talking about. So consider a graph. I would denote graphs by G. A graph has a vertex set and an edge set. This would be the standard letters for that. And then consider a graph. And I will not be drawing D plus one-dimensional pictures, but the general idea is you have a D-dimensional graphs of individuals who may be infected or not. So there is a degree n Tx can be either 0 or 1. 1 means that at a given time, at that point, we have infection. So the site is infected, and 0 otherwise. And now we are thinking of the history of that. So for that to describe, you look into this graph cross time, say R. Since it's awkward for me to draw such graphs, I will be drawing just the simple to draw one-dimensional example. So here is the evolution. Being an optimist, for me, time goes up, although I think that in mathematical studies of the contact process, often time goes down. That this will be the sites. And now, in the contact process, there are two things going on. In fact, that's the minimal process, contact process. There are more involved. You have a possibility of infection. Sites may heal. Healing rate is one constant. The other is infection rate. And the infection rate may be given by something which resembles our coupling constant. So it's coefficients Jxy. That's the rate at which a site X may infect a neighboring site Y. Healing rate would be, let me see, let me call it lambda. Yeah. And then if you can describe diagrammatically the evolution of this process by drawing the following space-time picture. Think of the healing process as a Poisson process of randomly occurring events in time, with the understanding that if the individual was not infected at that time, the healing had no effect. If the individual was infected, the healing event means that we transition to an uninfected state. But then, in addition to that, as long as there is infection at the site, it can infect neighbors, and that may be oriented on, that may be described by an oriented graph. And again, you can actually think of describe the infection in this situation, so in this process, as occurring potentially independently. So this event means that if this site is infected, at that instance it would infect this one. If not, then nothing happens. This is the advantage of having a process which is easy to describe. It's just the Poisson distribution of this of these healing events and transmission events. Then if you're asking what is the probability that a site at a given time t is infected, well, let's say you started from some infection at the initial time. The probability of it being infected the event of it being infected can be presented as by tracing back what we nowadays refer to as contact tracing. You go back and see where was potential contact. Let's say, well, in this case, there wasn't any, but basically you trace back all possible paths by which infection may have appeared. And the question is, does this connected cluster, now it's a connected cluster for oriented percolation, does it reach the initial infection? So in particular, if you would like to see whether the infection would die, even in the worst, starting from the worst boundary conditions, initial conditions where everybody is infected here, that becomes a percolation question.
Are you distinguishing healing and death?
In this model, let's see, death is a version of healing from the perspective of the, but it accords you permanent immunity. No such thing here. You have to keep on. So there are indeed other models in which there is also death, and I shouldn't say it loud, but when mathematicians discuss the contact process, when they talk about survival, they talk about survival of the virus. But let's not publish this fact. Well, all of that predates the recent, the influenza pandemic that we are still going through. So we probably are more sensitive to this now than we used to be. Okay, so this becomes a problem in oriented percolation, obviously. So that's a contact process. And again, what's the link of this with oriented percolation? In oriented percolation, you have a very similar model, except that the Poisson process is over not a continuum of times, but discrete times. We tend to formulate our lattices, our graphs, as discrete graphs. And now you may expect that if you chop the time into discrete intervals and you think of the evolution, say, from morning to morning, there will be a discrete version of this model, and it's natural to expect that in the big scheme of things, there should be no substantial difference between the behavior of these two. And indeed, that's the case. Although sometimes trying to write the...
Just horizontal lines cannot jump through verticals?
Yeah, so I did not draw it, but that's a good point. The reason I denoted it as JXY is that in principle you can have also possibility of infection which jumps across the neighbor, but it's just dependent on the distance. So it doesn't have to be nearest neighbor. Just like percolation models can be long range. Now, so one reason I wanted to mention this metric extensions is that when sometimes it's convenient for us to study the lattice version of the model, but first, the initial intuition and then experience, sometimes gain after time, teaches us that there is not really much difference between the discrete and the time continuous version. Let me mention also the continuum Ising models. So there are continuum percolation models. So the passing to continuum, if you have, I would draw percolation in the vertical direction. As I indicated, the continuum that I'm talking about is the trivial version of the trivial case of one-dimensional continuum. So in this case, the scaling limit is not very dramatic. It's rather easy to take, but it's still very it's worthwhile to be aware of how to do it and its existence and so forth. Mathematically, it's not as rich as the two-dimensional continuum limit about which we heard in the first lecture. So for percolation, the continuum version of it is totally trivial, because in a model in which the probability that x is connected to its neighbor, say, okay, x connected to y is equal to probability that nx y, the hopping, the edge is 1. That's our basic parameter p in percolation. A continuum version of that is you think of percolation occurring unless there is a blockage. So think of the events of percolation occurring in the presence of random events of blockage. And in that case, if those events are Poisson distributed, if you take an interval, the probability that there is a connection is just the probability that there is no blockage there. So that would be 1 minus e to the minus beta, where beta is the Poisson density. Right? I hope that what I'm saying is clear. If you have a collection of points with Poisson process of intensity beta, the probability that you have exactly n points is n to power beta, is beta to power n over n factorial times e to the minus beta. The probability that there is no point there is e to the minus beta, and the probability that there is at least 1 point is that. So that actually fits very well with the way we sometimes like to present the percolation density as 1 minus e to the minus beta, because that accords us a convenient differentiation parameter. That's just a side comment. Okay, so the Poisson, the passage from discrete to time continuous percolation is trivial. Something similar happens for Ising systems, although slightly the correspondence is slightly different. So in percolation, it's Poisson with p equals 1 minus e to the minus beta. Now, in case of Ising, and that's closely related to Ising's original contribution to the subject, which was not very big. If you take an interval, let's see, with spin-spin interaction, if you just have two sides, x and y, I'm drawing my graph vertically, the correlation between sigma x and sigma y is, of course, a hyperbolic tangent of beta times this coupling x and y. Now, you may to have a continuum process which reproduces this, you just notice that if you chop this interval into n segments, then sigma x, sigma y is the product of over j from 0 to n, sorry, from 1 up to n, of sigma u j, sigma u j minus 1. This is just a telescopic product of pairs of spins, which leaves you only with the endpoints. And then in one dimension, the expectation value of that factorizes, because these are independent random variables. So to produce this particular correlation between the endpoints, the elementary observation is that the strength of the interaction that you want to have between the nearest neighbors should be cranked up, so that this, just a second, up. Yeah, the correlation neighboring spin correlations have to be very correlated, because otherwise you get exponentially small correlation between those. So basically, this would be with couplings Jn, and Jn actually tends to infinity approximately as log n over some constant. I think it's 2 beta plus some function of beta. So in other words, there is a continuum Ising model. You can think of a continuum Ising model for which the interaction across an infinitesimal interval dx is very strong. It's strength which has a logarithmic singularity. So there is a bit of singularity here if you try to write it in terms of the coupling constants. That actually has been one of these confusing things in describing the continuum, which I may come to later. Okay. Now, how are we doing with time here? So I would like to mention some. So I'll come later to example. Oh, actually, no. Let me do it now. Yeah, let me do it now. Other examples of this sort of diagrams. So, ground states of quantum systems. To study the ground state of quantum systems, what you often want to do is take trace of e to the minus beta h times the observable that you're interested in, divided by e to the minus beta h. Take the limit in which beta tends to infinity and the volume diverges in the appropriate way, order. That's the ground state or a ground state expectation value of the observable A. Now, here is a general way to deal with such things. Let me start from the trivial fact e to the minus beta h, not to have too many minuses along the way, let's just call it as beta as e to the h. And here is an identity which is kind of trivial, just power series expansion. This is function of h is entire. It has a, actually, sorry, so let me put beta, excuse me. E to the beta k minus 1 can be written as summation n from 0 to infinity, beta to power n over n factorial, e to the minus beta k to power n, power series expansion of the exponential. Now, that's how you look at it in calculus. No, I think that's still correct, but thank you. So a probabilist's way of reading this could be to notice the following, that what we have here is the operator k, and this is true for operators, not only for real valued k. It's the operator raised to some random power, and the distribution of this coefficient is nothing else than the Poisson process. It's the probability that the Poisson variable takes value n exactly. So one way to depict this is to, again, think of an interval of length beta and consider a Poisson process of points distributed here. Poisson process means that the occupation of different sets are, the occupation numbers are jointly independent. And that's one of the nicest, sweetest distribution of a random integer. So this is k to some random power. Now, if k happens to be sum of terms, as it is in our situation, in many of the models of interacting particle spin systems, you have your graph, the vertex set of the graph G. K would be sum of interaction terms, which I denote by alpha. So alpha stands here for a pair of neighboring sites, U and V, one of the graph edges. If you apply this formula there, then it's very natural to actually, well, with each such point comes k, which is a sum of terms. It's very natural to actually expand this in the following way. Just draw here a vertex, take the cross of the graph, cross product of the graph with the interval 0 beta, and what you obtain now, sorry, I'm not. Let me know if what I'm drawing is not visible. That would save me some time. So what you obtain now is, again, something similar to what we saw in the contact process. It's a random scaffolding, which is obtained by having the ranks distributed by a Poisson process of intensity 1. We keep intensity 1, but take beta to infinity. And again, these are independent Poisson, independently placed ranks. It's a random scaffolding. And then, so out of that, you get the following trivial observation, that trace of e to the minus, sorry, not trace, e to the minus beta as an operator can be presented as, yeah, thank you, as an integral rho of mu d omega. Omega would now describe this collection of randomly selected ranks. Let me denote them by their position in, as an edge at time t. And then for a given realization, what we now should really do is take the time-ordered product of operators which are associated with those rungs, you let the time run up, and you take, what you should do is take the time ordered product over times, the event alpha t in omega of the operator k alpha. That's a generally valid representation of e to the minus beta h. And now if you want to take the trace of that, well, you would need to do the trace of this. By linearity, it's just mu d omega trace of that. And if you would like to insert an operator a should appear here. And to make it concrete, one way to evaluate the trace is take your favorite basis and sum over vectors of the base of vectors you selected. So it's summation over, now this would be, sigma would refer to collection of, say, sigma z x, that you get an orthonormal basis by looking at vectors in which, say, the z component is diagonal. So it's some of those spin states, sigma, and then you have this product k alpha a sigma. That's the quantum expectation value. That has to be normalized by the partition function. That's the expectation value.
And sigmas are signs plus or minus 1? Or?
Yeah, so sigma can be signs plus or minus 1 of the Z Pauli spinor. And you sum over configurations where you start from sigma and end at sigma. And to see what you get, what emerges out of it, well, let me take an example which actually would link to the Q-state Potts model, on which we have a number of experts in the audience. So here is a specific example to demonstrate this principle. Let's see, I should write now some operator. In fact, you get two interesting classes of quantum operators by starting from the Heisenberg model. So, of course, what enters here, sorry, let me explain where I'm heading. What we try to understand what's going on, you now want to try to trace the values of that. So first consider the case where there is no operator A involved. You start from some spin configuration, and then you hit it in this random sequence of times by operators which are associated with those edges. And the amplitude which you get is exactly the amplitude for the operator between these two spin states to some new spin states. And you have to sum over the outcomes of that. So the rest now details, of course, on the nature of this operators k alpha. And just to have an example of what can come out of that, let me go back to the Heisenberg Hamiltonian and consider the following. Well, actually, well, the Heisenberg model, I would write in this particular way, sigma u dot sigma v. Now, think of sigma now as, oh, the notation is atrocious. Sigma u would be a triplet of Pauli matrices, which are usually denoted as x, y, and z. So since x, y, and z are attached to the spinor matrices, I try to use for sides the letters u, except when I flip to x, y unintentionally. So my apologies for that. But that would be some of the neighbors, say u, v neighboring sites. And for what I'm saying to be correct, let me do the following. Let me take factor of 2 minus 1. the reason for this gymnastics is that as you know, this is related. This operator sigma u sigma v is in correspondence with the value of the total spin of the sum of the two spinors, and the total spin can, in this case, if you have two spin 1/2 vectors, the total spin can be either 0 or 1. So that can be written as constant times sum of the projection on the singlet space of the spins at u and u plus 1. Now, if you take it in this manner, if you consider the generalization to higher spins in this form, you may be interested in the extension of this to more general spins. And in the general case, the projection on the singlet of two space of the sum of two vectors, now of magnitude s, can be written as sum of the following rank 1 operators. It's sum over m prime from minus s to s minus 1 m plus m prime. And then we have the so, as you know, what we are listing here are the z components of the quantum spinors. For the two spins to add to 0, that has to add to the two have to add to 0. So the spin values are the z components are m and minus m for the two neighbors, and what I'm describing here is essentially a rank 1 operator which transitions between that value being m minus m to m prime and minus m prime, so that it preserves the total. And that's a representation for that. So if you do that, coming back to the operator which I drew here, what you obtain, I guess it may be simpler to reproduce the graph here. So the matrix elements of this operator, other than this oscillatory factor, essentially require the incoming spins to add up to 0, m and minus m. The outgoing spins would be m prime and minus m prime with no other amplitude, no factor which depends on those two. So these are independent. So if you're asking what's the consequence of this, what does this tell us about the partition function of the model, you discover a surprising relation to Q-state, classical Q-state models. Because to understand what configurations would be compatible with that, with these rules, what would actually contribute non-vanishing value to the trace, what you may do is associate with this configuration loops. You start with a spin, the initial spin here, it's constant until it's hit by an operator, and then the matrix elements of this particular operator provide no information on what would be the spin. This spin can flip to anything else, but only if the spin at the neighboring point actually had the reversed value. So basically, if you draw a loop going up and then reversing orientation going down at the other end, for a trace you have to consider only time periodic loops. So that whatever was the value here, it has to be also along this line, and again now reversed along this line, and so forth. You trace the constraints by drawing a family of loops which eventually have to close. So that's not perhaps the most exciting example, but of loops. But if you look at general configuration, what you obtain is a random dense. It's a dense system of loops. And then when you look into the statistics of the spins which are associated with that, it's very simple. Along each loop, there is a value, the value has to be maintained consistently, either up or down, depending on which way you go. And otherwise, there is no correlation between the values of those. So from this, what you learn, the formula tells you is that the partition function of this Heisenberg model is equal to, well, this is no longer Heisenberg, but this model, let me call it H1. Well, at this point, it's the only one. So this would be integral over mu d omega. The trace, well, the trace would be sum over all the initial configurations, which coincide with the final configurations, which are consistent with that. And the consistency would tell you that you have 2s plus 1 possible values raised to the number of loops of omega. Okay. That's the partition function of this, model H. And the expectation value of, let's take the z spin at z at u times z component at v, that would be the average of sigma zu, sigma zv in an ensemble of randomly placed loops, which are then assigned random signs. And then you see that something very simple happens. Under the event that the two are not connected, the spins are totally decoupled, they are uncorrelated. So, and when they are connected, they are rigidly tied together. They are either the same or of opposite sign, depending on the parity of the distance. So this actually is equal to, let's see, -1 to x minus 1. Oh, that, what I'm describing is an antiferromagnetic Heisenberg model, incidentally. I'm not sure about this sign. I think that I wanted the antiferromagnetic model. That was -h. So it's this times the probability that the sites u at time 0 and v at time 0 are connected with respect to omega. Probability in this ensemble. And at this point, many of you who are, those who are familiar with the Q-state Potts model would realize that this is very similar to the Potts model's statistics, except for a couple of differences. First, that's true for every Q. Sorry, quantum mechanically, you get 2s plus 1. So the relation to Q-state Potts models is that 2s plus 1 corresponds to square root of Q. Because the Q-state loop systems give you square root of Q to the number of loops if you count the loops which encircle the clusters as well as the dual clusters.
What happened with the signs? Do they drop out? This -1?
That's an excellent question. We are very still rather, our mathematical abilities are more limited when it comes to signed measures. So it's extremely helpful if because of the topological constraints of the model, the signs actually wash away, and they do so. So there's a simple kind of counting here which shows that contributing configuration, these signs actually add up to 1. I mean, multiply to 1. But that's an excellent point to pay attention to. So there are a couple of differences with the Potts models. One is that the obvious that we have taken the continuum limit in one direction, not the discrete model. That's what we talked about before, just like is the contact process. The other is that
should the x minus y be u minus v?
F minus y. Oh, yes. Thank you very much. Absolutely. Yes. Thanks. Right. So the other difference is that in the Q-state Potts models, the lines, the loops are the boundaries of connected clusters, and the relevant question is whether the two spins are within the same cluster. What flips independently there are the spin values assigned to clusters. For this quantum system, the partition function is the same, well, up to this trivial change between discrete and continuum model, except that what matters for quantum spins is whether or not they are on the same loop, the same boundary. Again, curiosity. But now, now related to that, I'm somehow presenting a hopscotch of ideas, and the time is running so fast that I probably keep hopscotching. This brings up another interesting observation, which is important for Q-state Potts models as well, and that is when you have a dense system of loops, it's very natural to ask whether the family of, whether in typical configurations, when you take the double limit beta to infinity and space to infinity, whether in this infinite system, typical configurations include infinite collections of nested loops or not. And associated to this are height functions for which these loops represent the level lines, they are oriented level lines. So now, whenever you see dense packed loops, actually not even dense packed, whenever you see, no, sorry, it's simply in dense packed. No, sorry, the dense packed is relevant but not essential for this. So if you have a system of non-crossing loops, it's a relevant question of whether the number of loops encircling a point is finite or not. If it is finite, you can immediately conclude that there is symmetry breaking. Because if the number of loops encircling this point is finite, the parity of this number here between neighboring sites would differ. So just by the fact that you have a finite collection of loops encircling each point, from this you can conclude that there is some observable, at least initially formulated in terms of the loops, for which you have translation symmetry breaking. The observable is the parity of the number of loops encircling the site. You then ask yourself, is there some more physically observed quantity which would exhibit this symmetry breaking? And the answer is yes. It's related to the question of what is the total spin when you sum spins over a long segment to the right of a site. So let me not get into the details of it, but the upshot is that this mathematically meaningful but physically not initially obvious symmetry breaking actually translates into a measurable symmetry breaking in terms of measurable quantities expressed in terms of spins. You see, what's going on here is that we have spins which to some extent are more visible to our experiment, and then there are those loops which may be pigments of our imagination as we think about it. Symmetry breaking in one does not necessarily have to imply symmetry breaking in the other, but it does. So to continue with the sentence I started, option one is that you have finite number of loops with, of loops encircling any given point, and that translates into symmetry breaking, or else, now, or if not, then so what I'm trying to describe now is the dichotomy. If not, then the two-point function has to exhibit very slow decay of correlations. So what we get here is a dichotomy. Either a long-range order and symmetry breaking, or, and what comes out of this is that, you see, if there are infinitely many loops, consider sum over pairs of sites u to the right and v to the left of the probability that they are on the same loop. So the indicator function, which says that u and v are on the same loop, adds up to infinity when you sum over u to the right and v to the left. And that means that the sigma z correlation in absolute value diverges. But by translation invariance, that is the same as divergence of sum over n of the correlation between, say, the spin at 0, z at 0, and z at n, absolute value. So let me just finish the sentence. And so what I'm saying is that in this model, by virtue of this representation, you immediately end up with the observation that these systems, in a way which may depend on the value of beta and q, sorry, not beta, value of q, should exhibit one of these two phenomena.
So you are apparently at zero temperature, otherwise that would never be long-range order.
That's right. So I'm talking about beta to infinity, otherwise the number of loops encircling a site would be finite always. So now we are talking about dichotomy about a certain quantum spin chain. And if you wish, what it says is as follows. It either, the divergence of this corresponds to what is also referred to as vanishing mass gap, because the correlations do not decay exponentially. The mass gap is the gap in the spectrum of the transfer matrix. So you either have degeneracy of the ground state, or vanishing of possibly two states corresponding to the symmetry broken phases, but each with zero mass gap. So it's a physically interesting observation which comes for free. And then you may ask, well, for what value of S would that happen? And seeing the relation to the Q-state Potts model and hearing about results which were already mentioned, you may guess that Q equal 4 would be the relevant transition point. And indeed it is. So the transition between this is you have symmetry breaking if Q is greater than 4, or if you wish S greater than 1/2, or else if it's less or equal than 4. So in the Heisenberg spin 1/2 Heisenberg model, you have this situation. For higher spins, you have that. I'm sorry, but the time is running very fast on here in this place. There are other things which I wanted to talk about, other common features of a range of models. I do not know whether it's really a testimony to the unity of science or mathematics, or to our limited imagination, perhaps. But one more comment about that is trying to explain the why Q equal 4 is the special relevant value. Let's see, just a second. Yeah, well, that's a result which for Q-state Potts model was known since the work of Baxter, but he known in the sense of physical prediction. But even Baxter pointed out that he would welcome rigorous justification of the assumptions which were made in his calculation. And then the justification came in the work of Hugo Dumniu-Copin with Vincent Tassion, Sidorovicius, Manolescu, Harel, Gagabedian. Beautiful theory emerged of that. But yet another chapter was added to this when it was realized, I think, by Gurav Ray and Inon Spinka, that you can explain the special value of Q by the fact that this particular weight for the Q-state Potts models, again, that's something which was probably noticed well before by Bernard and colleagues. If you write Q, square root of Q as, let's see, probably I want to write this as, give me some letter, Y, no, let's say little q plus, no, sorry, e to the tau plus e to the minus tau. Write it this way. The computation of the number of loops is a very non-local, at first sight, is a very non-local calculation. You have to look at the global structure. But you can translate this into a stat-mech type of quantity, which is product of local terms, by assigning to these loops weights which depend on the turn which are made. And for that, you write square root of q in this manner. And then the relevant point about q equal 4 is that that's the point at which tau changes, the solution of this equation change from real to imaginary. This change was indicative that something happens here, and that's the relevant. But how to do that? Well, that was, there's a beautiful argument by Ray and Spinka, which allowed to turn this into a mathematical proof of this discontinuity, which, as I said, was wrestled by Hugo Dumnier-Coppen with a collection of authors I mentioned in another beautiful piece of analysis. But there is a explanation of this through this argument, and turning to this quantum model, and that's now a joint work with Hugo and Simon de Wartzel. It turned out that you can build this argument for this ensemble by hopscotching between the Q-state Potts model, the quantum model, and yet another quantum system, which is very different, for which the phase transition is not long-range order of this type, but actually phenomenon of dimerization. Oh, no, sorry, actually, dimerization is actually this one. But the phase transition I'm talking about in this case corresponds to the quantum dimerization, but I would not get into this now. I should stop in 2 minutes. So reviewing what I wanted to say, half of it was not said, but that's life. Let me mention in passing another recent work, which I mentioned here. Yeah, that I'd like to mention this just as another example of the value of this continuum extension. Villain model. In more recent works, sorry? Yeah. No, I'm not talking. No, I am 5 minutes within the gap because we started 10 minutes later.
3 minutes late.
Sorry?
Time is precious.
What does the chairman say?
You have your 2 minutes.
I have 2 minutes. Yeah. So the 2 minutes which I want to use, just to present another beautiful extension example of this, is the Villain model, the partition function of the. So I'm now talking about the O2 spin model, for which the partition function by Villain version, is essentially integral over angles. The spins sigma are given as e to the I theta, and the integration is over angles, and the partition function has a product over the edges, and then sum over integers k associated with each edge of e to the minus beta over 2 summation of essentially the difference n u minus n v square shifted by an integer which here I called k, or 2 pi k square.
The angles have disappeared.
Thank you. This was angle. Thank you very much. Theta u minus theta v plus 2 pi integer. Okay. Now, I just want to make this point. I won't go into the detailed discussion. This is a recent paper. But this can be seen in a very natural way as associated with a model which is really formulated on the metric graph. Think of the angle theta as performing a Brownian motion on a circle. Then the amplitude for returning to given values would include a possible winding number. So in this case, the Villain model can naturally be viewed as associated with a collection of Brownian bridge amplitudes along the edges, constrained by the whole thing making sense in terms of angles defined at the vertices. From this perspective, you may ask, what is the continuum limit of? What is it a continuum limit of? And the kind of universal relevance of Brownian motion via central limit theorem suggests, and indeed that's not difficult to fill the details for, that the Villain model can actually be viewed as a limit of discrete XY models, whose coupling is driven to infinity, just as the Ising model's coupling had to be driven to infinity if you want to have a model with slowly varying correlations. So the Villain model can be viewed as the continuum limit as delta x tends to 0 of the XY models. And that means that certain tools which were known to us about XY model, like the Lieb-Simon inequalities, which produce another dichotomy for the systems, apply also to this. So that's a subject which I'm not going to talk about, but I want just to mention that there has the interesting phase transition for the O2 models is the Kosterlitz-Towles transition, whose existence was proven by Fröhlich and Spencer, which was proven simultaneously to the phase transition of delocalization in the integer-valued Gaussian field. The two were proven by related tools, but now there's a new there's a set of new observations which tie the two directly by another route, having to do again with this sort of considerations. So the relevant works which I would like to mention here are by Marcin Lis, who produced a new beautiful proof of delocalization of integer-valued field, kind of discrete fields. The proof was limited to graphs of degree 3, but it was extended by us to general graphs. And then proof by Dietrich van Engelkenberg and Marcin Lis of what we showed by other methods also, that at any beta for which the dual model delocalizes, you have slow decay of correlations for the O2 model via mechanism which is very closely related to this topological one. So that brings me to a point where I should stop. So thank you very much. And I'd like to, 1 more minute.
So, I think one question
about the blackboard which is behind, like behind this one. Like, yeah, can you raise this? Yeah, so I wanted to say so you said for Q larger than 4, the transition is first order. So I wanted to say that in physics there's this conjecture that if you take Q just tiny bit above 4, then there exists a tiny perturbation of the Fk measure, which is there exists a tiny complex perturbation of Fk measure, such that the transition again becomes second order.
Complex, let's see.
It's complex, but it's tiny, so maybe it's within reach.
Well, Dobrushin was brave enough to look into partition functions of systems with complex couplings, and his analyticity results in this way. So that would be very interesting. Is this something like a metastability related?
No, it's not metastability. It's supposed to be stable. It's called complex CFT.
I would love to learn more about it. Thank you. So just by metastability, I meant the continuation in case of first order transition. But we should
no. It's more robust than that.
I see. Okay, sorry.
So yeah, in a Q equals 3 state path model, for the nearest neighbor, you have a second order transition. But if you allow your range to grow a little longer, you'll get a first order transition. And I'm just wondering whether you can see it this way.
Yeah, let me first expand on the question. we are used to talking about universality, and it's taken for granted that short distance, various parameters do not really affect the critical behavior. For example, JXY, nearest neighbor or not. In case of Q-state Potts models, that's not the case. So the fact that Q equal 4 is the magic place does depend on planarity. And we did not venture much beyond this, but that's a very natural question. In any case, it is not, it's known, in fact, that, that you lose this special nature of Q equal 4 when you go beyond planarity, when you spread the interaction. And eventually, it should be the relevant quantity to look at is the mean field calculation. And for the mean field, if I'm not mistaken, Q equal 2 may be the relevant point.
One other question, if I may.
I want to make another comment after that, but after you.
So can you see with this representation, I mean, one expects to see for the antiferromagnetic spin 1 model a gap, right? So can you see, how is this gap
for
realized?
this one?
Yes. Antiferromagnetic spin 1, right?
Yes.
Not spin a
yes.
half, but spin 1.
Spin 1, yeah. You see a gap. You can prove that there is a gap. And the gap, you can prove it somehow, by a similar argument to the proof that the Q-state Potts models are gapped.
You can prove it at all temperatures?
Sorry.
No,
no, hold on. I just a second. Just a moment. No, hold on. Sorry, excuse me. I'm talking about Q less than 4. Less than 4. There's too much noise in my head at the moment. Let's talk about this later. There is one other comment which I want to make on, if the chairman permits me, and that is 2 remarks. First of all, this place has played a very special role for many of you and for including me. Many of the developments which were mentioned and those which were not, in many instances were stimulated by visits of participants to IHES. So that's one amazing feature of this meeting for me, the right place. Next, the mix of ages here is also fantastic, I think. Again, for me personally, it includes my mentor, my PhD advisor, Joel Leibovitz, then some of my all-time collaborators, Fröhlich Spencer, with whom we interacted both here and elsewhere, but there were some very meaningful contacts here. And then I've been lucky enough to, later in life, to encounter brilliant young people like Hugo, who revitalized the field. And then my more recent collaborators include even students of Hugo. And so it's, I think, fantastic to have this mix of ages. And then not only Ising model celebrates birthdays, but also some individuals do. And in fact, on our way here, we marked Joe Leibovitz's round birthday. Not round, but a birthday. And 20 years ago, on a somewhat similar younger occasion, a special issue was produced of Communications in Mathematical Physics dedicated to Joel. And I happen to have a copy of that, which was unsigned. So I brought it here and invite all to join their signatures. It already has quite a number. With a dedication to Joel, in celebration of your recent birthday, and with deep appreciation of your impact on our science and mathematics, and decades of steady commitment and multiple contributions to our community. We wish you many happy years and interesting science to come. Joel.
Thank you, Michael.